Good morning, everyone, and thank you for joining in. Thank you very much to the organizers as well for arranging this much needed event. It's an honor to be among such eminent panelists and discuss the future of construction industry across the globe. This is Azhar Ali Siddiqui, BIM manager with Hatch India, and today I'm going to talk about an issue that is close to my heart, not just as a professional, but also as a person. The issue that I'm talking about is climate emergency. It is not just climate change now, it's already changed and is an emergency now. More than just providing solutions as construction professional through this presentation, my end goal will be towards raising awareness amongst architects and engineers in organizations about these issues and its solutions. And by raising awareness, I do not mean to have an understanding about how greenhouse effect works, but to understand, truly understand the urgency of the matter and start acting now as humans first and then as professionals. Right. So this is a pie chart over here that talks about a contribution to the extreme weather events across the globe. And I just want you to focus over here. I don't want you to be confused by the enormity of information that goes in here. I just want you to focus over here the energy used in buildings, 17.5% energy used in buildings. Now, this is 17.5% responsibility of saving the world, 39% responsibility of controlling the greenhouse gases. Now, these numbers are considerable and should be enough to get us moving. Right now, the demand is growing every day, no doubt about that. So we must build, that is for sure, but we must build sustainable to stay in the game for a longer period of time. Now, sustainable. What is sustainability? Well, it's been over a decade now, and we've been hearing this term almost everywhere. You go to H&M, they will say that the T-shirt is sustainable. You pick a water bottle from a store, you will find the word sustainable written over it somewhere as well. You open any organization's website these days, if you do not find the term sustainability written over somewhere on it, I will offer free beers to any Irish pub of your choice. Now, that is a tall claim, I know that, but I can do that much to have a beer with Ralph, to have a long conversation with Ralph. Bottom line, sustainability is the buzzword, and if anything becomes a buzz, often we tend to forget the true meaning. If we tend to forget its true meaning. Now, you ask anyone these days what is sustainability, and you'll probably get the answer that it is about being environmentally conscious, which is wrong. In fact, environment just constitutes one aspect of sustainability, other two being the society and the economy. So, for a product to be truly called sustainable, it not only needs to be environmentally beneficial, but also take care of the society and the economy. Right. The solutions that we are going to discuss today revolve around this very definition and has this explanation. For an engineer or an architect to be truly build something that is sustainable, they need to have a thorough understanding of the basics of sustainability. Because without this base, without this basic knowledge, it will be just another programming or designing job. And this is not just another programming or designing job, but a fight against climate emergency. Right. So now let us understand how BIM can aid the inclusion of sustainability in the use of buildings today through a few case studies. Now, over here, these are some of the applications that are born out of amalgamation between BIM and sustainability. We are going to discuss them in our case studies, some of them in our case studies. Right. So these are some of the sustainability requirements from clients in the industry today, and they're growing. They're growing almost each and every day, getting more and more demanding each passing year as we inch closer towards the ambitious net zero goals set by the respective countries for their respective infrastructures. And as I mentioned, clients are getting more and more demanding. Here is one of the examples that we are going to take, and this we're going to take this as a first case. I just want you to focus on the blue box over here, and the requirement in this case from the client was to bring down the heat gain from the envelope to less than 1 watt per square. But now, how do we quantify such a thing? They wanted 80% daylight space. They said zero glare, and it is only the envelope depth performance that we are talking about. And this is where BIM as a process, along with its modeling and simulation tools, comes into the picture. Right. So in this case, there was a site, and on one side we had three buildings. Over here, you can see these are the glare analysis result in front of you, where you can see the glare component was extremely high. Building A and building B, they're still in control. But for building C, it is just out of limits, going over the roof. The solutions, of course, we do have solutions for that, putting the shading devices, using glasses of suitable types. But how do we make the selection? Right. So as a first solution, we decided to go and play around a bit with the type of glass that we are going to use on the facade. We ran daylight analysis with 40% VLT glass, a low VLT glass, checked for compliant daylit areas. They were not meeting the requirements of at least 80% daylit space in the office that was set initially by the client. We moved forward and checked with the 50% VLT glass. Improved results, but still not enough. Now we were running simulations continuously with using the different types of the glass. Then we decided to run daylight analysis once again using 60% VLT glass. Building A and B, you can see, were well within the compliance range. Building C, almost there, not exactly how much it should be, but it's almost there. We decided to stop here and combine this with other solutions and figured out that we can always come back, increase or decrease the VLT, run analysis once again accordingly if requirements are not met, and see if 60% is sufficient. Another thing we did over here was to design the shading devices for the facade using parametric mapping. So what we did over here is that we optimized these parameters in such a way that the shading is provided for the required areas of facade. Now we ran multiple iterations for those parameters. What should be the optimum spacing, optimum angle, and optimum values for different options of shading devices. We looked for results in terms of the areas covered and the sunlight exposure. This was done for the shading devices of the facade for all around the building, and checked for the best case scenario year around. Right. So these are the few iterations that you see we ran for this particular shading device, and on multiple iterations and discussions amongst architect, mechanical engineer, and sustainability consultants, we basically were able to get these results. And as you can see, the parameters are optimized on further discussion with the integrated design approach team, and we made sure that the glare component and the energy concerns are addressed without compromising the daylight requirements. And you can see each and every parameter is tailored for precise need, resulting in proper shading, along with saving in terms of the material cost, right? So this is the glare analysis result after the consideration of 60% VLT glass, and using the shading devices that we designed in the previous step. We combined both of them. We combined the results from using 60% VLT type glass, and we combined that with the shading device, with the parametrically designed shading device that we just saw in the previous slide. So the glare on the building A and B, as you can see, is addressed and is in control now. For building C as well, we saw some sharp reduction in the glare component, but still, it's still above the required limit. So we decided that we will move forward with 75% VLT glass type. Over here, as you can see, we picked up the 75% VLT glass type, ran the daylight analysis once again, and combined the results with the shading device. We were able to satisfy 2 of the 3 major requirements over here. We were getting 80% daylight space along with the reduction in its glare component. Now we had to take care of the envelope load. For that, we decided that we will optimize the window to wall ratio in conjunction with the optimization of U values of the building envelope. Right. So we started by comparing our options with ASHRAE's baseline. As you can see over here, we decided that we'll compare our options of window to wall ratio. What are we supposed to get? What are we supposed to use? And we'll compare that with the ASHRAE baseline values. And of course, greater the window to wall ratio, more will be the annual energy demand. So we have to keep it low, but also, keep in mind the daylight requirement. So it's a trade-off, basically. A complex one to get, no doubt about that. But this is where BIM comes into the picture as a process, sets up the base for this trade-off by making iterations, a lot more quicker and accurate as compared to manual calculations. Right. So we decided that we'll move forward with 69% window to wall ratio, keeping in mind the daylight requirements and decided that we can always come back and make adjustments if the envelope load goes, uncontrollable even after further optimization in the U values. Then finally, we optimize the thermal insulation of the building envelope, and that is basically the U value. We optimize the U values for external walls, roofs, fenestrations, and we also checked one. This is for roof, this is for fenestration, and then we also checked one for the fenestration with shading devices as well. Once we had the best case scenario U values that were less than what the ASHRAE baseline had to offer, and we had to keep it less than that because we were aiming an envelope load of less than 1 watt per square feet, which is close to 25% less than what a conventional building generally possesses. So we made our recommendations based on different capital cost in case of the multiple options. For example, if you see there are multiple options and recommendations over here, so selection was made based on the different capital cost of these multiple recommendations. And finally, after interdisciplinary discussions, multiple iterations later, we were able to generate this recommendation table over here. And this is for the overall envelope load. Here as well, we compared our recommendations with ASHRAE recommended baselines, and all of these recommendations for U values, in combination with the selected window to wall ratio, use of the shading device that we designed in the previous steps, proper glass type selections for facade, all of these solutions, when used in combination, they helped us in achieving the initially discussed requirements, thus giving out a sustainable solution which is not just environmentally beneficial but is also economical and catering to the comfort of the society. Right, so this was about our first case. I'll quickly move on to the second case of the day, and this is a case of improving the performance of a basement, basically. And we generally design a lot of basements. This was a standard basement. This particular case is one of my favorite just because of the amount of simplicity that simplicity of the solution that we provided for this. Now, this was a standard basement. Over here, we performed the conventional basement ventilation calculations as electromechanical engineers. And the owner, by the end of the design, they wanted to reduce the energy consumption if possible. And in terms of the lighting and ventilation fan capacity, they wanted that if we can improve the energy efficiency of both these systems. So, as recommended by architects and sustainability consultants, we decided that we will provide 4 cutouts around this building, right? So we decided to provide 4 cutouts around the building, put louvers on them, and see how that helps in getting the daylight inside. So we made those changes in the model, ran a daylight analysis for those cutouts, and figured out that these results that you see over here, the basement was close to 56% daylit when opting for those 4 cutouts. Now, while we were doing this, we also ran a wind analysis simulation for the same 4 cutouts that we just saw in the previous slide. So we observed a strong breeze flowing in through them. Now, this was a result. It was resulting in natural fresh air flowing inside the basement, and we instantly decided that this can be optimized for better results. Right. So upon further integrated discussion with the mechanical engineers, architects, and sustainability consultants, we strategically increased the number of cutouts. Over here, you can see the strategical location and the increase in the number of cutouts and strategical placement of these cutouts. We tested for their best placement possible, and then we place these cutouts in the model as well. So using these optimized cutouts, we again ran daylight analysis simulations. And once again, as you can see over here, we are getting close to 85% daylit areas in the basement, practically eliminating the use of artificial lighting to a large extent during daytime. As you can see over here, it's 85% daylit, and that practically eliminated the use of the artificial lighting over here. Also, in case of fresh air as well, and this is how the cutout looked like inside. Also, you can see that picture over here, that these are the cutouts with the louvers that we place. Also, the basement ventilation resulted in huge contribution from the natural fresh air flowing in. And as you can see, apart from that blue zone in the bottom, almost all the basement was properly ventilated. Now, this resulted in reduction in capacity of the ventilation fans used and saved a lot of money on operation cost, and obviously on energy as well. There were energy savings as well. So again, this was all in all a very simple solution of providing cutouts and making the use of basement making the basement use truly sustainable. And as you can understand, we are again hitting the triple bottom line of sustainability by setting the all three aspects, namely environment, society, and the economy. Right. So I'll quickly move on to my third case study, and I hope I'm not dozing you guys off. So this was a this is going to be an example of a net zero building, and you know, a net zero building is always challenging, no matter what. Those who have idea on about how that works, how that design, and how the consumption and the production quantities are matched, you guys might have an idea how difficult and how challenging it can get. So this was even greater challenge for us because, as you can see from the image over here, that was a small building of 45,000 square feet only on a 800 square meter piece of land going 45 meter tall. So basically we had very less area. The biggest challenge in this case was that we basically had very less area to place our solar panel. The optimum and the best location for solar panels generally is roof. And since, as you know, it was a very less area for the solar panels to place, it was a huge challenge for us to, generate energy using these solar panels. Now, and what we did over here as a first solution is that we analyzed the sun path of the building throughout the year to identify the shadowed area so that we can put the solar panels at the best location possible. We determined a trapezoidal area where no shadow was casted and decided on building the car park over there. And we decided that over that car park, we'll put on the shades, and over those shades, we'll place the solar panels so that the best case incident radiation can be tracked using those solar panels. So apart from that, we studied the solar radiation of the facade. We decided that we would wrap the facade with solar panels all around. And we decided we will generate from all four sides of the building, and from the roof, and from the parking shade as well. But easier said than done. The aesthetics, the daylight compliances, glazing requirements, and energy concerns, all of them pose their own challenges. Now, what we did over here is that we ran multiple solar analysis with multiple designs of solar panels on all four sides to pick the best optimal solution. We studied incident solar radiations year round for all the facades. We looked at the solar exposure, which is number of hours in the days solar incidence is happening. Then once we figured out how sun is behaving with the building, we went on towards the daylighting scenarios, different design of solar panels on the facade. Now, initially, when there were no solar panels on the facade, the building was close to 100% lit, as you can see over here. Now we started putting solar panels in different angles, sizes, and shapes till the point when the daylight requirements were sufficient, and there was sufficient daylight areas in the building, and we also had to take care of the maximum energy output production. So it was again a trade-off that we had to carry off using multiple iterations, multiple options going through, and again the daylight requirements had to be balanced with the energy production as well. And also we had to take care of the amount of heat that is coming in through the building, through the facade. So after all these options after all of these options of placing the multiple solar panels in multiple orientations, we finally came to this recommendation over here. We gave various options for placement of solar panels, basically in detail, where we determined the angle, shape, size of solar panels, how are these parameters going to affect the glare, how is it going to affect energy production and consumption. All of it was determined upfront. Now, finally, and as you can see in this table as well, there are multiple options for just one placement of solar panel. For Southeast, there are multiple options to pick from, and we could pick the best incident radiation by running multiple simulations, by multiple iterations of the same solar panel all across the year. So finally, through balancing all four aspects, namely the aesthetics, the daylight compliances, glazing requirements, and energy concerns, we were able to generate 228 megawatt hour of energy with an effective EPI of 67 kilowatt hour per square meter per year. So this is pretty good. We were able to generate a lot of energy with just a small building, and this was pretty good. But this was just the first part. Second was to design the building in such a manner that the consumption matches the production, and for that we use those previously discussed active and passive design strategies. And as you can see, through over here, as you can see over here, through the step-by-step approaches based on design suggestions and strategies by architects and engineers. We were able to match the consumption patterns with what we were producing to reach the net zero performance. And here, as you can see, this is how the building looked like after we wrapped the whole building with solar panels in different angles and orientations. So yeah, this building is in Kolkata, operating right now. It's not exactly a net zero model, but not a net zero building, but we're close to getting what we wanted to. And at the end of the day, most importantly, it's not affecting the environment in a bad manner. So yeah, that's it, ladies and gentlemen, from my presentation. I hope I was able to convey the right message across, and I'm open to questions now. And before signing off, before I sign off, I would like to take this platform to urge and spread the word. I would, I would like to request each and everyone to, spread the word about climate emergency and in your organization, because I feel only a motivated architect or an engineer can take this challenge as a responsibility and not just, work on it as another corporate exercise and, limit it merely as a jargon, just like we have been doing for a lot of things out there without actually knowing the true meaning of it. So yeah, that's it from my presentation, ladies and gentlemen. Thank you very much for being so patient and listening to me. And yeah, until next time.